Okay, my first time doing this, so that's another good reason to show up, because if these are bad, you guys were here in person to see it. So, okay, it looks good on my thing, so on my phone, so I hope it's good. Okay. All right, so this is Fluids, Lecture 1. It is January 5th, Monday. We already went through intros, canvas, and syllabus, so now we're just going to go through Chapter 1. And that's basically going to go through some pretty simple stuff. A lot of you guys will probably know these properties from thermo. It's just going to be the characteristics of fluids, some units and dimensional analysis, and I am a big fan of that. When I used to work at the QSC, the tutoring center, when I didn't know how to solve a problem, like units alone would kind of guide me to how to get to the answer sometimes. So, fluid properties and ideal gas law. Okay, so Chapter 1, like I said, you can read in the textbook before class, or you could do it after. But here are my slides just complementing the textbook. I basically read it myself, and I tried to condense it so what information I think is important for you to know, and then what you need to solve the homework is going to be in here. So like I said, units, fluid properties, compressibility. We're going to talk about viscosity, vapor pressure, and surface tension. So pretty cool stuff. So I guess my intro to fluid mechanics. I told you guys I'm a Boeing stress guy. Why am I teaching fluids? It was the class I got to teach. but you know, I don't know if it's just when my friend groups, they think I'm the nerd. Like, I hope you guys love engineering, but just knowing how things like this works is just so cool to me. So that's what I hope to present to you in these lectures, is not only you'll pass your exams and things, but hopefully you get to learn actually something that you find interesting that you could bring up, next time you go to Canada, you could bring up with your buddies. This is pretty cool. And then, you can kind of intrigue them when you're in Canada doing whatever you're doing. Okay, so fluid mechanics is literally everywhere that we kind of walk around in engineering. Gas, liquids, or fluids. Literally for Boeing, how planes work, we use Bernoulli's equation for a wing, right? The pressure is higher below the wing than above. We're going to learn that later. Gases, anything hydraulics and vehicles, right? We're going to learn all of that as well. And you can divide fluid mechanics into two ideas. Here's how we're going to learn it. We're going to have fluid statics, basically at rest, and fluid dynamics, moving. So chapters 1 and 2 is going to be on the static portion, and then a lot of it's going to be dynamics. So once we get to Bernoulli's equation and the Navier-Stokes equation, it's going to be the dynamics portion. Okay, and if there's any question, just feel free to interrupt me. We don't have to be too formal here, so. Okay, characteristics of a fluid compared to a solid. And it's kind of just for a concept-wise, like how do you characterize what a fluid is compared to a solid, right? So super simple without even knowing like anything about fluids, right? It deforms compared to a solids. And we're going to look at this figure down here is when you have a surface of a fluid and when you apply a force, a lot of our force analysis is going to be on shear stress and shear forces. So compared to a fluid and a solid, the molecules are really spread apart. And you guys probably already took chemistry, right? Compared to a solid. So that's why you can drop things into fluids and pour them out. Solids, like if I drop like a steel block or something, molecules are really compact. It's not going to move around. Okay, so smaller intermolecular forces, like I said, those are the molecules that actually hold everything together for your fluid. So in solids, they're really strong. That's why you can't really break apart a solid, right, without actually a big force that gets past the Young's modulus, right, in that stress-strain curve. So, and then it takes space of their containers, right? So that's pretty obvious. If you pour a fluid into your cup, that's going to take a shape. If you pour a solid block into your cup, it's not going to work. And it deforms. So this is the big one from the textbook that will say, what's the difference between a solid and liquid? It deforms consistently when acted upon a shear stress of any magnitude. And that's big, right? Because if I have a fluid in this cup, I pour it out on this table. If I put a shear stress, it's going to deform in some way. You guys took mechanics and materials, right? If I have any specimen, I apply shear stress, unless it gets past that yield point, it's just going to deform back to its original state, right? So I guess that's the big difference here, is for fluids, you don't have to really worry about that too much. Okay, so units and dimensional analysis. I'm not going to go through this because you guys are probably experts at this, right? We're going to try to use all units, at least working here, right? We're going to use English units, but right, SI units is my favorite. So you have your normal newtons, meters, kilograms, Kelvin for absolute temperature, and we're going to go over what absolute temperature is. You have British gravitational BG units, Rankine, you guys should know that from thermo. It's another absolute temperature. You have your slugs for your mass in that units and feet. EE units is similar to BG units in terms of, but usually in terms of force and mass. That's why you have your pound mass and pounds, but you still also use feet. Yes?
Are the feet between British gravitational and English engineering the same? I just want to make sure.
Yes, it's the same. Yep. Yes?
Slugs the same thing as a pound mass?
Oh, good question. What is your name?
McKenna.
McKenna. I was ready for you, McKenna.
McKinnon, not McKenna.
Oh, McKinnon.
That's my cousin.
McKinnon, okay. So here is the big difference here. A pound mass and slug explain. I have this hidden in case nobody asked. So it's basically a pound mass multiplied by the gravitational force, right, which is 32.2. And that's the main difference, where a slug is equivalent to 32.2 pound mass. And I have this slide in here if you want to look at it later. Good? Other questions? Wow, I was making that last slide. I'm glad you asked that.
Could that also be considered like pound force as well? One slug would be like 1 pound
Force. So I believe a pound mass in those units. So pound force is usually you multiply it by the gravitational force. Yes. Pound mass, when I say one slug, if you have F equals ma, that's literally just the m for a slug.
Okay.
Yeah. Okay, we're going to continue here. There's this table in the textbook. I'm not going to go through this, or too in detail, right? They have your length for L and T for time, and they're just saying all of these, right? Your normal acceleration, density of what units it is. FLT, I believe, is force, length, time system. So and then there's MLT, which is mass, length, time system. And the only difference, right, when you multiply the mass by gravity, right, your acceleration to get your force. So I'm not going to go through this, but this is basically the units just in terms of your length and time and force or mass. SI prefixes, you guys should be familiar with this. I'm not going to go through that as well, right? If you have a kilogram, it's 10 to the third. If you have a micrometer, it's 10 to the negative 6. And that's pretty big when you do problems. Just make sure you apply these properly. I'm going to skip this. You guys are probably experts at that already too. Okay, pretty basic stuff here. This is density for fluids. We're going to use Greek letter rho. Units is mass per unit volume. So mass, right, is going to be kilogram, slugs, or pound mass. And going back to your question, that's why it's not pound force, right? Pound mass is specifically for the M and F equals ma. And going back, these feet are the same. That's a good question, right? These are going to be the same. They categorize the mass of a fluid system, and the density of gas is greatly affected by pressure and temperature compared to other fluids. So you'll see in the textbook, I don't have them up here, because like I said, I kind of summarized it for you. You'll see graphs of how gas is changing based off pressure difference and temperature difference. And I'm going to probably go through this more, but right, if temperature increases, the molecules are more spaced out, so the gas is able to evaporate and kind of move more freely. We'll learn that about our vapor section. Compared to colder temperature, the molecules are vibrating less and they're really still. And you'll learn that once we learn about absolute temperature and what sub-zero is. So this is pretty big to use in if you have an equation sheet. I have a summary of equations at the end, which is similar to the textbooks. Specific volume is volume per unit mass, which is also the inverse of density. So this is like the money equation. Write this down. Okay. Like I said, I post these, so no biggie if you miss it. Okay, no questions. So you'll see in tables 1.5 and 1.6 properties of liquid. We just talked about density. We're going to talk about specific weight, viscosity, surface tension, and vapor pressure and bulk modulus today. And that's like a lot of stuff. That's why I just wanted to do chapter 1 today. So you can write in your notes, tables 1.5 and 1.6 is where you get these properties. When homework was really tough, right, we had to look for these tables and find these properties, but you guys already have the solutions to them. But it's still good practice. If you take your FE exam, you're going to need to know how to find properties for your questions, right? So I wouldn't take it too easy because we gave you the solutions. So I'd note these tables. Okay, specific weight we define by Greek letter gamma. That is gamma right there, that Y-looking thing. And it basically characterizes the weight of the system. And then its units is weight per unit volume, right? So weight is a force now, right? Go back to the original question. It's not a mass. So we have pounds and newtons, right, over the volume. So specific weight is related to density using gravity. So here is another important equation. Gamma is equal to rho, the density, times the gravity. Here's an example I put, right, just in units. You have your kilograms, meters cubed, just because we're talking about units this lecture. Meter squared, right? And then this is F equals ma. That's newtons. Then your volume is right at the bottom there. Okay. Specific gravity. In the table I showed earlier, they just called this SG, so there's no Greek letter for it. And it's defined as the ratio of density of the fluid to water. And it's basically just a ratio of your density here times the density of water. And the density of water is usually taken at 4 degrees Celsius or 32.2 degrees Fahrenheit. Alrighty. Hopefully I'm doing good giving you guys time to write notes. I remember when teachers went so fast you missed it right away, so. Okay. Okay, so what we just talked about was specific density, weight, and gravity. And if you go back, if you write them down or look at lecture slides, they're all kind of interrelated. So once you have calculated one, you can probably calculate the others. The main common denominator or value they have is density, which is rho. Okay, any questions before we go to ideal gas law? You guys should be experts at this because this was a thermo thing, I think. If I remember, yeah. Okay, so ideal gas law just is an equation to define the relationship between your pressure, P, density, and the temperature. It models gases under typical conditions when not approaching liquefaction, right? So that basically means gases that's not going to go back and condense into liquid. Gases are highly compressible compared to liquids, meaning you can compress them in a small space compared to liquids when you can't, right? That's why hydraulics work. So equation, right? P is, this is big too, this is absolute pressure. You guys already know this. Rho is density, R is absolute temperature. And I'm going to talk about the difference for absolute pressure and absolute temperature just to give you guys a quick review. And then R is the gas constant, which is in these tables here, 1.7 and 1.8. And then this is just, this new here is specific volume. And we're going to do one example problem of this because I actually found an error in the textbook. And I was kind of not upset. I was like disappointed because like this is like a 9th edition. It's a new textbook. I was surprised that they messed up on that. So I'll write the equation down here. We're going to use that in a second here. So tables 1.7, 1.8, that's the gas constant you'll see right here. Right, your English units and your SI units here. Okay, absolute pressure versus gauge pressure. So absolute pressure is measured relative to the absolute zero pressure, which is basically means it's a perfect vacuum when you're doing absolute pressure. And standard sea level atmospheric pressure, you probably saw this in thermo as well, right? 101.33 kilopascals. And they do this parentheses ABS in your textbook and problems just to show it's absolute. Or 15.696 pounds per square inch, also absolute. So, and compare that to gauge pressure, that's measuring the pressure relative to local atmospheric pressure, which is, right, what I just explained here. So for example, right, a gauge pressure, because it says gauge, how I think about it, is literally the pressure you measure in your tires. You have a tire gauge, that's how you measure it. And to calculate, this is not in the textbook, I just wrote this here, but you guys already know this as well. Absolute pressure is equal to gauge pressure plus atmospheric pressure. So if you need to go back and forward from absolute to gauge, you just add or subtract your atmospheric pressure in the correct units, obviously. Okay. Absolute temperature is where zero is absolute zero, meaning particles have minimum energy in motion. I kind of think of it's funny, I don't know if it's still popular. I used to play a lot of Mortal Kombat. There's a character named Sub-Zero. And I think about it in his moves, right? Sub-Zero is literally where it's so cold that nothing is moving, right, anymore in that block of ice that you're in. But apparently that's not fully true. They're still vibrating at a really small minimum level. So that's why it says minimum energy in motion at zero. It's just that cold. So absolute temperature usually expressed as Kelvin or Rankine, right? So Kelvin is in Celsius. To get from Celsius to Kelvin, you add 273.15, Rankine 459.67. Probably boring you guys. There's a lot of thermo stuff, right? You guys probably did this a lot already. Okay, so this is the example in the textbook that I found an error in. So compressed air tank has a volume of here, 0.023 meters cubed. This is the air tank. The temperature is 21 degrees Celsius and atmospheric pressure is at 101 kilopascals, okay? Find the density and weight of the air in the tank when filled with an air gauge pressure of 3.45 bar, okay? And that unit bar is, I believe, just a conversion for 100,000 pascals. Okay, and I think, so everyone here's had Dr. Bridge once before? Okay, so he's really strict on doing your given, finds, and assumes, and that is awesome. I think it's still needed for your whole engineering career. So I'm gonna leave the givens there. I'm gonna just find the finds here. I'm trying to make sure it's in the camera, but. So we wanna find, right, your density and then your weight. Right, and let's put this as W. Okay, so if we want to find density, right, we just want to make sure it's clear. We solve this for rho, so you have, oh, this marker's not good. So we'll have, okay. We'll have rho is equal to P pressure over R times T, right? And then you have to convert it, right? It needs to be absolute temperature. So we already have our P, which is, hopefully you guys can see because I'm on the right side here. So your P is going to be atmospheric pressure at 101 kilopascals, and then you have this. So you're going to add the two pressures together. So 3.45 bar, right? And if you do dimensional analysis, this is going to be 100,000 pascals over 1 bar. And then you're going to add your atmospheric pressure, right? Because you want to get to your absolute pressure. That's why we have that there. No questions. Okay. I have this on a slide here, so if it's too far, you'll see it here in a second. So add 101 kilopascals. Okay, so that's the numerator there. And then our denominator is going to be your R value, right, which is in the tables that I showed you earlier. And the temperature is just going to be your 21 degrees Celsius plus, was it 273 to convert to Kelvin? So let's just fast forward here so you can see it better. Right, so you have your bar, your pascals, your atmospheric pressure, you have your R constant here, and then you have your temperature, which is converted to absolute temperature in Kelvin, plus 273. And the error in the textbook was they did 15 to the 6th power to convert bar to pascals, where it should just be 10 to the 6th. And here's like another reason why units are so important, right? Because that's kind of how I found the error. And a lot of problems you can solve just based off of dimensional analysis, right? So if we kind of just do some simple dimensional analysis, just for this part here. So I guess we're trying to get to kilograms over meters cubed, right? So kilograms over meters cubed is our goal. And the numerator is pascals, and a pascal is Newton per meter squared, right? So I'm just going to skip that step. Right, and then you have your joules, kilogram, and Kelvin. Joules is from physics, right, is a Newton times meter, work times force. So that's going to be Newton times meter over kilogram, right? And then technically you can take these kelvins, or kilogram, right? You can extract those kelvins out, so it's just going to be K. One second here. Let me make sure I have those units right for the R constant. Yeah, that should be K. Right. Thank you. That kind of, yeah. Good call. I'll fix that. I was like, wait a second, Kelvin's not canceling out. So I will need to move this down here. Okay. So you solve this right. Kelvins cancel out. Your newtons will cancel out. I'm sure you guys already see it, right? So then it's going to be kilograms left with meters cubed. Okay. And that's how just units itself can kind of get you to the problem. And that's how I caught that error in the textbook. Okay. And here's the next part of the question too, was find the weight of the gas, right? So weight is just equal to rho times g. And then sometimes you'll ask, like, where is that equation from, right? Well, if you just do the dimensional analysis, you'll already have it right here. So, right, density, kilograms per meters cubed. I'll just write the units here and skip the math. Right, and then meters per second squared. And then the textbook, this is where they messed up. they did not put this volume in there. So then I was sitting at home at night, I was like, why do they only have this and this? That doesn't make newtons. So this is where the textbook messed up, if anyone's reading it. Right, so now your meters cubes cancel out. You have your kilogram, which is your mass, your acceleration, F equals ma, your favorite equation, and that's your weight, right? So that's your weight. Okay. So just a dimensional analysis example while finding an error in the textbook for ideal gas law. Any questions? That's okay with everybody?
Would it be fair to add volume in our equation, like the weight is equal to density, gravity, and volume?
Oh, sorry, yeah. I guess I made the same thing that, another error there. Okay, I will fix those in slides. Thank you. I will write it over here to remind myself before I go. Slides. I will do Kelvin in denominator. Weight equals to rho g volume. Okay. Thank you. Add that. I guess I got this because I was going off the textbook. Yeah.
So would that be different from specific weight?
From what?
The specific weight?
Right, because, right, so specific weight is if you just have it divided by the volume. So you could just take the volume and write back, divide that by volume, you get specific weight. Good question. Good, how are we doing on time? 9:48. Okay, my goal is to hopefully get you guys here out by 10:15. I hope. Okay, let's keep going along here. Went through that. Okay, so viscosity, this is important because one of your homework problems is on this. Just without even looking at the slides, right? Viscosity, you just think of the thickness of the fluid, right? So water compared to oil, oil is more viscous because it is thicker, right? It doesn't flow as easily as water. So we assume this no slip condition. This basically means if you have, I'll leave this up here. Everyone's good with this? You want to take a picture if you want, but it'll be in the slides. Okay. Okay, if you have like a tube here, right, and you just have water flowing in this direction, no slip just means that the fluid does not stick inside the tube. The fluid sticks to the tube, or else the viscosity won't work, right? So if you were to do homework, solution's already given out, so it won't matter too much. You would write this in your assumptions when Dr. Bridge does given, assume, find. That's one of the assumptions that you would put down. Okay, so like I said, it's the thickness to a fluid or resistance of flow. I already compared oil to water, just to explain to you guys. So dynamic viscosity is represented in Greek letter mu. It says the internal resistance to flow. Units are newtons times seconds divided by area, meters squared. Okay, we are mainly going to be using this dynamic viscosity, but textbook has kinematic viscosity. And they use nu, Greek letter nu, which is kind of annoying, but you guys are used to this engineering stuff, right? They kind of crisscross variables like that. But if you're solving your problem, you'll know what it is. So how fluid flows under gravity while factoring density. So that's why this nu is equal to dynamic viscosity divided by density. And higher temperatures usually mean less viscous fluids. And why I wanted to bring that up, like a real world example, has anyone changed their own car oil here? Right, so you have different weights of your oil. You have your 5W20 or 10W. So sometimes those changes from winter to summertime, right? And you guys probably know this already. But in colder temps, right, you want your oil to be less viscous and thinner, because when you start your car, you want it to get through the whole system really quickly, and everything's cold, all the molecules are really small, it's hard for that oil to get through your whole car. But in the summer, when it's really hot, for fun fact, I also autocross, like it's like a racing around the cones. You really push your car really hard, your engine's really going. You need a thicker oil to have more lubrication, which is a more viscous oil. So that's why, kind of engineering-wise, right? Thicker oil for hotter car temperatures, thinner oil for wintertime, so you can get to the colder spots right away. That's kind of a fun thing you could kind of apply in real life stuff. Questions on this? Okay, this slide's important because I think I have like a little hint slide at the very end of what slides apply to which problems. I was writing this and I was like, you guys can't get through your homework without some certain slides, so I added this in. So the viscosity equation is we're going to lead to this, but how it's derived, summed up, is this diagram here. So we're going to talk about this Newtonian fluid shear stress, and I'll explain what Newtonian fluid means. But if you have this diagram right here, this is how they got this equation. They have a fixed plate, kind of like an experiment, you could think about it. This brown-orange part, in the textbook, they first describe it as a solid, but it's eventually going to be a fluid. And you have a plate at the very top with an applied load P here. Okay? And this plate, when you have the applied load, you have your shear stress going the other direction. A is just the plate area. And right, that's why I was always saying shear stress is very important when you're comparing a solid to a fluid, because they're applying shear stress there. So I just want to tell you where it comes from. If you space out, this is what you need. Okay, so once you apply that load, right, this little u is velocity of the fluid, big U is velocity of the plate. As you're pulling it, you can see the velocity of the fluid is increasing as you get to the plate at the top. B is the distance of, I guess, your fluid, and Y is the distance as you're going up. Okay? So how that all relates, right? So this graph, well, I guess let me jump into this. You have your A and B line. As you pull this, you're going to have B prime, because B is going to shift. You have your delta B, right, which kind of shows there's a difference in an angle here. So as that's changing, the rate of change of as you pull this fluid and how this U changes with this Y, it's linear. And that linearity is why we call it a Newtonian fluid. So you can think of this kind of as like your shear stress diagram, stress strain diagram for your mechanics and materials class. So your shear stress is tau here, which is coming from up there, right? Your mu, here they're just dividing it by 1, but mu is basically going to come from the slope of this line. The x-axis is basically a derivative or a rate of change of du to dy. So that's basically saying as this u is increasing with respect to as you're going up towards the boundary of the fluid. Another way to say it is as this little u velocity of fluid is increasing as it gets closer to the boundary condition of that solid. Okay, so like I said, this is what you really care about, and that's how it's derived. This is basically just a y equals mx plus b equation. Your b is technically 0, right? This is your mx, right, in your mx plus b equation. And I have, like I said, a little cheat sheet hint thing of which problems you're going to use this for in your homework. Okay, let's see, we're doing on time, 10:31, you're joking. Oh no. Okay, my phone, okay, we're doing okay. Okay, bulk modulus. This, I actually don't think it's in your homework, but I wanted to summarize it for you from the textbook. It's how easily can a volume of a given mass of a fluid be changed when there is a change in pressure. So you just look at these diagrams, ignore the writing, right? Here's your volume, you have your pressure. Once you have your pressure, you have your change of pressure here. It's that dotted line, right? Then you have your volume, and this is your minus your change of volume. And from what I remember too, in your mechanics of materials, you have a bulk modulus for like a solid, right? So this is kind of similar to that. So dP is your change in pressure. Don't get scared by this Greek letter with the line crossed through. I don't even know what that's called. That's what the textbook uses, but that is basically your differential. It's like a derivative change of a volume over a volume. And the negative sign is due to increase in pressure. Typo. Sorry. Bulk modulus typo. Okay. Increases in pressure, it decreases in volume. And like I said, I don't think you have problems on this, but I just wanted to share that with you, that's there. And I think I'm a fair guy. If we don't really do homeworks or we barely talk about things in class, I'm not going to put it on your exam because I've had teachers that have done that before. I don't think that's really fair. I've had teachers who make you derive a new version of a formula, like it's all qualitative, not quantitative. If I were to even do that, I would give you guys a heads up. So, okay. Vapor pressure. I think this is another, okay, we're coming up on a big one here, but vapor pressure is also important. So ignore the writing. I always like to go to the picture first. And why I'm teaching it like that is from the QSC2, they taught us this, is like how you should read textbooks is you should read the key topics they show, skim through the pictures first, and then go back and read. And it makes you understand more, because if you're reading about a picture you don't even know what you're talking about, it's really hard to understand. So this is pretty simple, right? It's just a liquid and you have a cap here. So if you have a liquid that starts to boil, right, you get vapor, water vapor, right? I think in thermo they call it liquefaction, is right to the point of when you're boiling your water, it's going to turn into gas. So once you get this water vapor, your pressure for this is going to start exerting upwards, right? Because you have your liquid, the water vapor, exerting pressure on this metal cap. You can think of it as like a water container too, right? If you ever seal hot water with a cap on and you have like a little opening like this, if it's really hot, you're going to hear a pressure change just really quickly from that. So that's what this diagram's kind of showing. Okay. Evaporation occurs when liquids like gasoline and water is exposed to the atmosphere. So if you naturally leave a water out, right, it's going to dry by itself. You guys already know that. But at a more in detail level, the molecules at the surface of the water have enough momentum to break the intermolecular cohesive forces, right? And that's the forces that's holding your liquid or your fluid together, which leads to evaporation. So those waters turning to gas, they have enough momentum to escape these forces, which is why they evaporate and create this water vapor. So when a liquid like water boils with a lid, I just explained that, vapor pressure notified by V subscript B is exerted on the lid, and the pressure is also exerted on the surface of the water. So it goes both ways. This could be found in tables 1.5 and 1.6. So this is a quick thing. You'll see in those tables vapor pressure. This is what it is when you think about it conceptually, when you just find it. So when you do a problem, you just don't get the value, you know what it actually means. Okay, questions are good? Okay. Really nice, easy example, right? A steam engine for your trains, right? So, right, in the movies, like Polar Express or something, they'll have fire coals, right? They're chucking it in, they have fire, creates steam, or it heats up the water, creates the steam. That vapor pressure will push this piston, and that's how you get your steam engine for your train, right? That's a really easy example. Wanted to get like an animated thing for you guys, but it wasn't working. So just imagine this guy spinning and pushing like that. Okay, so this is important because some of your problems will be on this. So surface tension, I think this is super cool. So like I said, like maybe I'm a nerd, but when you see like water in your cup, you see like a film of plastic, like how is that kind of there, right? You kind of just see it's not broken apart. You look at your water, you could just see there's like some kind of film or skin membrane at the very top. So it's a interface between the liquid and gas. This is water, liquid's down here, gas is above, where forces develop on the liquid surface. I'll get to this picture once we get to the bullet point here. So like I said, it acts like a skin membrane over the surface of a fluid. 10:02, okay. The molecules, so this is what explains this picture. So there's water molecules on the surface of this water, or it could be your whatever liquid you're working on. A net force is exerted downwards as you get deeper to the liquid. And that results into a net tension force. It's tension on the surface pulling down. And that's why that surface of your water exists. So if you think of water molecules here, I didn't want to draw a bunch of circles. It's literally pulling that downwards so you have that surface tension. So in the textbook, they have an example of, I didn't want to put it in here for a reason. They said if you drop like a needle or like a razor blade on the surface, it will literally just be upheld by the surface tension. But I was like, that's kind of a bad example because you guys just might think it's buoyancy, right? It's just floating. But here's a really cool example. If you ever see insects, right? These guys are literally so light that the surface tension of the water is keeping them upheld at the top of the water. I have never fly fished before, but if you guys think of fly fishing, this is what you're trying to mimic of this insect just going in and out on the surface of the water. And I think I read in the textbook, like these guys can go like 100 body lengths per second. I will probably double check that, but that was kind of insane to me. So that's how these guys are literally just standing on the water here. They're not enough to break the surface tension. Okay. It's usually represented by sigma, right? This sucks because this is a stress. So we're going to follow the textbook because we're using it for both sections. If I was just doing this myself, I would have had a different Greek letter. But yeah, I'll make it clear for you guys, like I said, right? If this is going to be, surface tension, sigma, I'll let you know. If it's going to be stress, I'll let you know, right? So units is also different, right? This is just Newton over a meter or a pounds over a foot. So a force over a length. Yep, units. You find these at this tables here. So we have homework problems on them, but I read in the textbook too. Many of the problems for surface tension is negligible because the other forces of your problem, such as inertia and gravitational forces, are more dominant than the surface tension. And that kind of makes sense, right? This example is only an insect on the surface. That's why other things don't really work, because they break the surface tension right away. Okay, questions? Cool stuff, I hope? Okay. Okay, so this is important. This 1.9 is because this, like I said, is going to be one of your homework equation for your homework problems. So this term, capillary action. So I had to look this up. This basically is a fancy term for a tube, a straw. I'll say straw. It literally has a hole in the top or bottom. And this is pretty cool too. It's like just your day in the life is just like you put the straw at the bottom. Depending what I'm going to explain here, sometimes the water will go up in the middle compared to decreasing in the middle, right? And why I'm going to explain this, because this will lead to an equation for surface tension. So before we understand how this works, we use these two terms, adhesion and cohesion. So adhesion is the liquid molecules that stick to the surface. Okay, so in other words, that's when you get your surface wet. If I throw this on this table, it's wet. Cohesion is liquid molecules sticking to itself. So just normal water sticking to itself. Okay, so in this example here, adhesion, the liquid molecule sticking to itself, is greater, liquid molecule sticking to the surface is greater than the liquid molecule sticking to itself. And that is how these water molecules, they're getting pulled up to the side of the tube inside here. And that's why you call it the inside of your straw gets wet. Compared to this here, when the adhesion, the liquid molecule sticking to the surface, is less than the cohesion, liquid molecule sticking to itself, it gets lower. So the inside of your straw actually doesn't get wet. So we're using water here, but they use an example also like mercury where it doesn't really stick. So this can't really happen. So that's kind of, if you see your straw and you see like water inside, that's kind of what's happening. And we're going to derive an equation, right? This 2r is just the radius times 2. This theta is the angle of this bottom of this meniscus, right? Bottom of this water, and then the angle of where that's occurring. In the textbook, there are 2 arrows here. I blocked one out because I thought it was confusing when you do your free body diagram. So I will show where this comes from. This is the free body of where we're going to get our equation. Any questions on how this works? Yes?
So if it was fully cohesive, it would be a slip condition?
Fully cohesive liquid. Yes, that's a good point. Yeah, because, and we can't assume viscosity, yeah, for the Newtonian fluid. That's a good point, yes. And going back to that, that is a good point I remembered. When there is no slip condition as well in different fluids, this is linear, right? A Newtonian fluid. If it's a non-Newtonian, these will actually start curving. So this is going to be a different, y equals mx. Yeah, this is going to be different. This is your y equals mx plus b. It's going to be like a mu squared equation or something. So this makes it easier because these are linear. No slip might make it different, curved. So yeah, good. That's a good point. Okay. So how this is derived, circumference of a circle is 2 pi r. And the reason for this is this is technically going around your whole tube, right? So there was an arrow here. I did the FBD. I doubled this for us, and you won't get the same answer. And I think the reason for that is, right, this circumference takes, if you're looking at your tube from the bottom, the water goes all the way around, right? So that's why that's just 2 pi r. Area of a circle is pi r squared. So here I'm defining it. Obvious for you guys, surface tension is this sigma, not stress, right? Units that we talked about is a force over length. Specific weight is gamma, which is units of force over volume, or newtons over meters cubed. So your favorite class in statics, I'm not going to go through too much of this because we're running out of time, right? Sum of forces in y. You'll, right? And I think Dr. Bridge always tells you to do this, right? And yeah, he's awesome. I love Dr. Bridge. He teaches you really good stuff. So you define your axis, right? So you guys are already used to statics. So if I had the sum of forces in y, I'm going to have this going up, right? 2 pi r sigma. Where does the cosine come from? It's opposite over hypotenuse, your favorite SOHCAHTOA, right? So that's where that cosine theta is, minus, right, your gamma pi r squared h. Why do these make sense? We're running out of time. I already did a dimensional analysis example, but if you plug what I had for these units into here, you will see that these are literally just forces. Okay? You do the algebra, move this to the denominator here, r on the numerator cancels, you get this. And that just defines the height. What time is it? 10:10. Okay. That defines the height of the water. Okay, so you can see they also mention, right? I don't know if your calc for, yeah, sorry, question?
Do we get surface tension from the tables where the properties of fluids?
Yes, they're there. Yep, they're there. Table, I think 1516, it's in the slides. Yep. Questions? Okay. So they call this inversely proportional, right? So as your radius of your straw gets bigger, the height decreases. And you can also play with this angle, right? So cosine of 0 is 1. That's, I guess, when you'll get your biggest. You can just play on your calculator if you have different angles. This angle is adjusting, and you'll see how that affects the height. Great. Any questions on this equation? Because this will be on your homework. But like I said, the solutions are there. Okay, good, cool. Okay, important equations in chapter 1. This is the summary in the textbook of the equations. I basically went through almost all of these. Good job, Elijah, except this guy. I don't think that is a problem in your homework, but yeah, you can just keep that in mind, right? Speed of light, just in the textbook if you want to see. Okay, so here's another way, because I worked at the tutoring center, right? You want to try to do these homeworks first on your own without looking at the solutions. That's probably obvious to you guys. If you just work at it side by side, you're going to learn a lot less. And the reason why I'm mentioning this, I'm going to show you some, it's really broad hints, but if you wanted to ignore this for now, so if you really wanted to solve it on your own, I just list the problem number here, and what section you should be looking at in the textbook. I also list these sections in the slides of what the equations are. This question 3 is a little bit weird. I will let you read this, and if you get stuck, peek at the solution. And then 1.9 is just what we just talked about. And yeah, I don't want to leave you guys stranded, right? I got you guys. I want to make sure you don't struggle on your homework. So this chapter 1 only goes, what we covered should get you through questions 1 through 5. There is questions 6 through 11 that will be based off chapter 2, which I will post a lecture on. And I will try my best because I will be in Colorado and I don't know how I'm going to do it really nicely on a whiteboard. Yes?
What does homework 1 do?
So, I don't know if I mentioned this in the syllabus. Homeworks will not be collected. So they're just there for reference for you to do good on the quiz. Homework 1 quiz will be next Monday. So I made that so you guys have a week at least to work it. Yeah, and I think that is everything from me. We did awesome on 10:14, just exactly where I wanted. So these 30 minutes we're going to use to watch chapter 2 lecture. Yes?
Is every homework 1 Monday for quizzes?
No. The syllabus changes because some Mondays we have off because of, I think, MLK Day or something like that. So some of them will be Wednesday. I will give you guys a heads up, but it's all on the syllabus right now. Other questions? Alrighty. Okay, you guys have a wonderful day. Nice meeting everybody. I'm really excited to have a nice quarter with you guys. So.
I have like one question.
Sure.
You spent time in like ASME and what's it?
SME. Yep.
Yeah. Was like any particular projects they were doing back then, or it's like
Yeah.
I kind of just wonder.
Yeah, we were just kind of trying to have a project for like a resume stat pad, we called it, kind of. So in ASME, we had ideas of 3D models of like those workout bicycles at the gym to create electricity.
Oh.
Like you use magnets and you use stator. We just made 3D models, nothing ever happened.
Right now, the current ASME, they're trying to work on like developing some sort of like small crane that can pick up Hot Wheels.
That's really cool.
I not gonna lie, in the feedback channel in the Discord, I've been urging them to like be more ambitious. Not gonna lie. It's
Yeah.
like, why just make like jet engines? Maybe I don't know. Maybe like I don't know. I'm more of like an ambitious person, but right now they're kind of like going simple, to be honest. But yeah.
Right. No,
They're trying to do stuff. We're trying to do stuff.
Yeah,
Really,
I agree. That sounds more fun.
As for me, I kind of prefer like the electronics club way of like they would just like if you and like two or one other person